Now we're going to work a couple of examples. The first one we're going to look at is the potential difference in a uniform field. This is very similar to the example that we did with potential energy, but it deals with potential only. In other words, we'll be looking at the points in space, not at the charges that we move between those points. So we're going to find a nice uniform general equation for this. And we're going to apply our rules. The electric field dot the displacement, negative sign. So we are starting at point A, which is why it's the lower limit on the integral. We're moving to point B, the upper limit on the integral. Our displacement vector, S, points between those two. However, this is a dot product, so we are looking at the component of E that is parallel to S, which is this dotted projection down here, D. So we can move from A to C and calculate the change in potential. Between C and B, the change in potential is equal to 0 because the displacement from C to B is perpendicular to the electric field. So when we find the scalar product of that, it's going to be equal to 0. So we plug all that in. Our cosine theta and E are constants as we move along that path. Integral a to b of ds, so that integral is just going to be s, which is the result that we have down here, magnitude E, magnitude s, cosine theta, as we go from a to b. However, cosine theta is equal to 1, because theta is equal to 0. Which just leaves us with the result, delta V is equal to negative E times D. Magnitudes, no direction. Potentials do not have direction. V is independent of the path. It depends only on the components of E and S that are parallel.